Hello everyone, my name is Horace, and in this video we're going to be going through LeetCode number 15, threesome. Now this problem is actually a sequel to the infamous LeetCode problem twosome. I've actually solved twosome on this channel before, so if you want to see the solution to that, you can find it in the description as well as in the LeetCode solutions playlist on my channel. For this problem, we're given an integer array nums, and we want to return all the triplets, so 3-element arrays, such that the indices are unique and that the elements of the triplet sum to 0. So as always, let's go through an example. We're given this integer array nums, and we want to find all the 3-element triplets such that the indices are unique and that the elements in each of the triplets sum to 0. If we look through the integer array, we can see that there will be exactly 2 triplets that satisfy these conditions. These are the triplets that contain -1, 0, 1, and also -1, -1, 2. And you can see that these both sum to 0. Now you might be asking how I found these triplets from the integer array nums. Now if we think about developing a brute force algorithm for this problem, we can simply use a triple loop that keeps track of the ith, the jth, and the kth indices in the integer array while we're traversing. Then we can simply check to see if nums of I plus nums of j plus nums of k is equal to 0. If it is, we simply append it to the resulting array and then return the array as necessary. Now an algorithm like this is going to have a worst case time complexity of O of n cubed. That's because we're using a triple loop for this brute force algorithm, and the time complexity for that will just be n times n times n, where n is the length of the list. Now O of n cubed for an algorithm is not the best, but we can do better. So to develop a more optimal solution for this problem, we can look at the brute force algorithm and see where we can minimize some of the repeated or unnecessary work that was being done. Firstly, it's important to go ahead and sort the integer array nums. This is because we can traverse the integer array easier and use certain properties to help speed up the algorithm. Now, a default implementation of a sorting algorithm is going to have a worst case of n log n. Then we can go ahead and traverse the integer array once and keep track of the current index at the index I. So let's say we have a ith pointer and we traverse the integer array. Then for the integer array to the right of the ith index, we can simply traverse this list. However, instead of normally traversing it with a for loop, we can use the 2 pointers method. So we can keep a left pointer and a right pointer at the start and end of the remaining integer array. The reason we do this is so we can get the elements at the indices I, L, and R in big O of n squared. Now while this algorithm seems correct for the time being, we also have to keep in mind that we cannot have duplicate triplets in the final array that we return. However, with such an algorithm, if we have duplicate elements, so for this example, we have 2 -1s, well, we can potentially compare these same elements twice. So for this example, we can compare 4, -1, and 2. But if we increment the left pointer, well, we might get 4, -1, 2 again. And let's say these were numbers that sum to 0. Well, we would be adding the same triplet 2 times. To avoid adding the same triplets twice, we can simply add one occurrence of a number. That means if we have multiple of these same numbers in a row, we'll just skip to the last one. We can simply do this by comparing the elements at index I with I minus 1. And if it's the same, then we know that the elements are the same. But if they're different, then we know that the elements are different and we can check that possible pair. And the same technique is used for both the left and the right pointers. And this only works because we know that the integer array is already sorted. Because the integer array is already sorted, we know that the element at index I plus the element at index L plus the element at index R, if it's less than 0, we know that we have to increment the left pointer. That's because the left pointer is going to have the lowest value in the integer array that's formed between the left and the right pointers. Similarly, if the element at index I plus the element at index L plus the element at index R is greater than 0, well then we just decrement the right pointer. And obviously if it's 0, then we simply add it because we know that it's a valid triplet. Again, the time complexity for this algorithm will be big O of n squared, and the space complexity will be big O of 1. Since we're not using any additional data structures, we're just using 2 pointers to keep track of the elements in the integer array. Now that we have some intuition as to the algorithm that we can use to find the triplets from the integer array, we can try and write the code for it. So we're on LeetCode now, and we can go ahead and write the code for the solution. As I mentioned earlier, we're going to sort the nums array, so we can just write num sort. Now sorting the array is going to take big O of n log n time, because Python uses timsort, and that's going to have a worst case of O of n log n. Next, we can initialize our result array that we're going to return at the end of the algorithm. Next, we want to just traverse the entirety of the nums array, but we also want to make sure that we're going to less, since we want to account for the j and k values. Then we can go ahead and skip over all the duplicate elements. So if it's not the first element, so if I is greater than 0, and the current index element is not equal to the one previous, so I minus 1, then we can write continue and just skip duplicates. Then we can initialize our left and right pointers for the remaining parts of the list. So the left and the right pointers are going to be at I plus 1, so 1 more than the current ith value. And the right pointer is going to be the length of the nums array minus 1. Then, since we're using 2 pointers, we want to continue traversing the list until they cross over. So while the left pointer is less than the right pointer, we'll continue to traverse. And we can store the triplet value as triplet, and this will be equal to nums of I plus nums of L plus nums of R. Then we want to look at the individual cases. So as we mentioned, if it's less than 0, we'll increment the left pointer. If it's greater than 0, we'll decrement the right pointer. And if it is 0, we'll add it to the result array. So if triplet is less than 0, then we can go ahead and increment the left pointer. If it's greater than 0, then we can decrement the right pointer. Otherwise, we know that it's 0, so we'll add it to the result array. So we can just append the triplets, so result.append, and we'll write the list of nums I, nums L, and nums R. We want to continue to skip over duplicates that we see in the remaining integer array, so we'll go ahead and write a similar code to the one above that we used to skip over the duplicates. So we can say while the left pointer is less than the right pointer and nums of L is equal to nums of L plus 1, meaning the one next to it, then we'll increment the left pointer. And while L is less than R and nums of R is equal to nums of R minus 1, since we're decrementing the right pointer, we'll decrement it by 1. Finally, we can go ahead and increment the left pointer by 1 and decrement the right pointer by 1. So we can go ahead and submit this code and see if it works. As you can see, it's accepted. So the time complexity for this algorithm is going to be O of n squared. Also, some sort algorithms use O of n space. So the space complexity might also depend on the sorting implementation that you're using. With that being said, hopefully you learned something, and I'll see you soon.